All right, now I want to show you how to make a survival curve like in the Lancet Public Health article where you're evaluating survival associated with a drug or a treatment, in this case for an opioid intervention or drug, using an underlying Markov model. So similarly like we did with sealants, we start with a state transition diagram where they're cycling through the alive state, and then each cycle they could either stay alive or they could move to dead. When you convert the state transition diagram into a tree, we configure the model here, and then it's a cost effectiveness analysis. Willingness to pay, let's just default to $50,000 per quality adjusted life year again, put the willingness to pay in there. And then, again, I just like to label the payoffs. So the first one, I always put cost in dollars, and then the second one, I always put effectiveness and quality adjusted life years. Now I like to also format them. I just want a few more decimal places in here, so let's extend it to 4 decimal places. You'll see why I wanted to do that later. The cost is in currency, effectiveness, I put a custom suffix, and then write quality, so you can see in the sample it shows that cost is in dollars, and then effectiveness is in qualities. It just helps us when we roll back it. And then make sure I put the decimal places for the difference between cost and effectiveness as well. Now I'm just building out the tree here, so I'm making it a decision. So we could choose between a drug and a placebo. So choosing between drug A or drug B, or choosing between drug A or, I'm calling it a placebo. In this case, it's just a comparator. It's just choosing between 2 different drugs or treatments or interventions. I always label the first part of the tree choose right there, and then the Markov model, that's going to be drug A. So this is going to be like a pharmaceutical intervention to address opioids. So a drug that treats opioid addiction or abuse. Now each state of the model, remember we said in the state transition diagram that it could either stay alive or it could move to the dead state. So in the last project when we had a sealant, it was either sealed or it was extracted. In this case we're talking about a person or a cohort of individuals. So alive is sort of an analogous to sealed, and then dead is sort of like a tooth being extracted. So remember, TreeAge defaults to 120 years or 120 stages or cycles of the model. I'm going to change that to 80. So I'm going to evaluate the effectiveness and the cost effectiveness of this drug over 80 years of a life course or 80 years of following a cohort. Now I just want to code up some variables here so we could use them later in tornado diagram and a sensitivity analysis, sort of replicate what they do in the Lancet Public Health article. I'm just entering all the variables here, so we're going to need to say the initial cost of drug A, and then we're going to say the final quality or quality adjusted life year associated with drug A. So let's set the final quality to 1 quality adjusted life year and the initial cost to $150. Now I want to make the probability that they're alive. So last time in the sealant example, with the tooth model, we defined what the probability alive is as a fixed number, as a value. Now I want to define it as a variable. So I'm adding more detail into the model. I'm saying the probability alive is a decreasing function of stage. So you see in root definition there it has a long complicated function that I put for probability alive. It doesn't really matter what specifically I put. What matters is that probability alive is some decreasing function of stage. So each year it goes through the cycle, each year of the model or each year it follows the cohort, there's going to be less and less probability alive, more and more probability dead. You put the Markov information for that alive state there, so initial cost, set that equal to the variable initial cost, which we said was 150, and then final effectiveness, we called that final quality, which we defined to be 1. Since I already said what probability alive is for stages 1 through 80, I could just go into the, edit the probability alive here and just set it equal to the variable probability alive, which we defined as that decreasing function of stage. So the probability that you're alive decreases every year. Every year that you're alive, you're more and more likely to die, less and less likely to remain alive. And just like last time with the sealant model, we could run a Markov cohort here and see all of those 80 stages. So it starts with stage 0, where everyone's alive, no one's dead. 100% alive, 0% dead, all the way down to stage 80, where 1.6% of them are alive and 98.4% of them are dead. So after 80 years, 98.4% of the cohort has died, or for an individual, There's a 98.4 chance that they've died after 80 years. You could graph that here. So that survival curve is like they show in the Lancet Public Health article. It just graphs those probabilities from the Markov tables that we looked at. And you could do that by hand. You could just take those probabilities from the Markov table, put it into Excel or a graphing calculator or whatever you have, and look at it as a survival curve. But the survival curve is only effectiveness. We want to look at cost effectiveness, which we show through the supply curve here. So remember, we have to decide whether it's cost effective to scale up the supply curve, spend more money per quality, and switch from a placebo to drug A. And here we see that it is. Remember, the net monetary benefit of drug A is higher than the net monetary benefit of the placebo, so we choose drug A over the placebo. Shows here it chooses drug A, highlights that in green, snips off the placebo. We say that drug A is cost effective compared to the placebo, given that the willingness to pay was $50,000 per quality. Now the tornado diagram is where we look at different variables in the model, in this case the final effectiveness and the initial cost of drug A, and we analyze the effect of these different variables on the ICER and on the net monetary benefits. So we give it a range. Final quality, we'll say it varies from 0.5 to 10 qualities. Initial cost, we'll say varies from $0 to $500. You can see the expected value there. That's the net monetary benefit of drug A. So it starts out the net monetary benefit of drug A and varies from there. If you look at the ICER, you can see the expected value. That's the ICER 9,684. That's the ICER that we got from the model, and it varies around that.